Oh, yeah.
I'm not feeling too good right now. You said the highlighted and bold words I have to...
Yep, rotational and line symmetry. Anything about those two things? What?
I've seen you misplace my book in my locker.
There's an extra one up there.
Thank you.
Mm-hmm. Okay, so we'll get back to the definitions, and it's okay wherever you're at. We'll give you, if you need to get some terminology right. Here's a look at this week. Today we're going to take a look at section 2.4. We'll finish that off. You'll have homework. About everybody got done in last period, so don't imagine you'll have much work to do. Tomorrow we're going to review, because on Wednesday we're going to take a quiz. So that's a big day for Wednesday. Thursday and Friday, of course, we'll finish up 10.1 and 10.2, and then, of course, after Friday, we get to enjoy a fall break. Okay, so make sure you're here on Wednesday for the quiz, and this is also the end of the 9 weeks. Okay. So that's kind of the outline for the week. You can see we're not doing a lot with the quiz. Quiz would be very similar to the last one, about 20 points, maybe 25 points. But that'll be on Wednesday. Okay. Okay, so now let's talk about section 2.4. It talks about linear symmetry, which is basically a line of reflection. Okay, so if I'm talking a line of reflection, if I look at a figure that looks like this, and I know that these sides are equal, then I've got a line of symmetry that could go right here. That could be folded right in half. Okay? But if I don't know that this segment's equal to those, would this also be a line of symmetry? Don't think so. Okay? What if I have a skinny rectangle? All right. Would this have a line of symmetry? Yeah, I think so. How about right there, and how about right here? But what about this line? Connecting the diagonals. Would that be a line of symmetry? No. It cuts it in half, like the area is cut in half, but it's not like if you would fold that on a piece of paper, it wouldn't match up. You see the difference? Okay. So that's a line of symmetry. What about if I were to rotate this 90 degrees? Would that be considered rotational symmetry? No. In order for it to be rotational, here's what I want you to think of. You guys ever played that game of concentration? I think it's called concentration. Where the timer goes off and the board is shaking, you got to put all the pieces in. Isn't that called concentration? It's an old time game. Maybe I'm showing my age. It's actually fun. You should look it up. But it's basically you got a short amount of time and you got to put all the pieces in the right slots. Okay? Well, one of those is like a little star. And you don't have, I mean, you can rotate it and put it in. You can pull it out. You can rotate it another way and put it in. You see what I mean? You could rotate it a lot of different ways and the star fits into the slot. Does that make sense? That's the idea of rotational symmetry. That if I pick up this block or this square rectangle, pick it up and rotate it 90 degrees and put it back down, that doesn't look like the original. What would look like the original is if I go another 90 degrees, so a total of 180, and it looks like this. So it would be, but not at 90 degrees, but only at 180. You see the difference? Okay. All right, good. Turn to page 102, and you're going to see a star. On page 102, you're going to see a star, and it's going to say 72 degrees rotational symmetry. Does everyone see that? 72 degrees rotational symmetry. And I'm not very good at making stars, so I'm going to try, but these are... I struggle with these. So, stars are tough to, I think, tough to design. Okay, so that's a equilateral star. Not very good, but that's an equilateral star. Now, how do they get 72 degrees, you think? Okay, so this is how. We know that in one revolution, all the way around, it's 360 degrees. So if we count the number of tips or endpoints of the figure, in this case we have 1, 2, 3, 4, and 5. In this case there's 5. So then we take 360 degrees divided by 5. And when we do that, we get 72 degrees. That make sense, lady? So if I were to pick this star up, turn it, rotate it 72 degrees, it would, and then put it back down, this tip would go there, 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 and this tip would go there. You see that? Everything, it would rotate like 72 degrees. But I could also start again, and I could go 144 degrees. So not only 72, but 144 degrees. Because I could rotate 144 and put it back in, and it would work again. Well, I could also go, because usually they want to know what's the rotational symmetry for everything less than 360. 360 makes sense because that's just all the way around. So if I go another 72, that's 216. And if I go another 72, that's 288. And so a star is going to have 1, 2, 3, 4 different angles of rotation or rotational symmetry. Now on that star, are there any lines of symmetry? I don't see any. I mean, it just kind of depends, I guess, how you draw it. Maybe in the middle, maybe like that. Flip it over. That'd be close. Could you have one at each tip then? It depends. If it's equilateral all around, yeah, maybe. Okay, let's turn it over to the top of the next page, which is 103. Fill in the blank here for example B. It says, determine whether each figure has rotational symmetry. If so, identify all the angles of rotation less than 360. So the first one they have, for example B, is a square. All four sides are equal, and they're all 90 degrees, so that makes it a square. Okay, so does it have rotational? Can we rotate this? Yeah. I think it has 90, 180, and 270. I think that one would have 3 of them. No. You could actually have an octagon, which would be 8 sides. Okay, so that's why that idea of taking the 360, divided it by the number of endpoints, helps you figure out how to do it. Okay, what about a triangle like that? Can this be rotated at all? Well, if we rotated it 90 degrees, wouldn't it just look like this? That's not the same as what you started with. You see what I mean? So now you got to try and picture that in your mind. But if we just rotated 180 degrees, it would look like, I don't know if that's quite a 90-degree angle, but it doesn't work at 180. You see that? So I don't think it has any. I'd put none. What about the arrow up and down? Well, if we rotated it 90 degrees, it would look like this. That's not the same. But what if we rotated 180? Oh yeah, 180 would work. What about 270? No. So you getting the idea of how to determine, okay, how many angles of rotation? All right, good. Let's. There are some things about describing the type of symmetries. Does it have linear? Does it have rotational? So turn to page 105. And I want you to do 6 through 9, fill in the blank. See if you guys can get these right. Okay, so page 105, 6 through 9. There's only two types, either line or rotational. So it could be either or, it could be both, or it could be none. Okay, let's take a look at these together. All right, number 6 looks like it's a square. It's kind of positioned like a diamond, though, because it's on a, it's tilted. One thing I do need to point out, naming a figure, make sure you go clockwise. So, like, if you notice, this is figure A, B, C, D. They don't go A, B, across C, and D. See what I mean? So once they start naming a figure, they always work their way around the figure. Same thing here. This is figure E, F, G, H, I. This is figure K, L, N, P, R. Yaba.
Why is it saying the book A, B, B, B?
Oh, they didn't print the C, did they? I don't know why they didn't. Because when they name it, it's A, B, C, D, right, in the figure. But the bottom, you're right, the bottom. That's not the first mistake we have in this book. I guarantee you that. We found all kinds. And then look at 9. It starts with T, and it works its way around. T, U, V, W. Okay? So don't go T, U, and then cross the figure and go W, V, or anything like that. It's not like reading a book where you go to the end of the line and you go back to the left and go, okay, you work your way clockwise around it. All right, so now back to the square. This is both line and rotational. That would be both of those. And then if I draw in the lines, let's see, I see this one. I see this one. I see this one. I see 4 lines of rotation. And then what are the angles? Well, we already did this, right? 90, 180, and 270. So those are all the things that you should have filled in. Line rotational, 90, 180, 270, and there are 4 lines. All right, let's take a look at this one. Okay, I don't see a line here. I do see that it is line rotation, line symmetry. I think the only one, though, is this one. Anybody have a different one that I'm not seeing? Okay, and then so there are no rotational. There's one. And then we would say there's no angles of rotation. Okay? All right, good. Let's go to number 8. Now, this is, I don't think I've clarified this very well. Let's look at this. What do these little dashes mean that they have right here and here and here? There's 5 of them. What do those little dashes mean? No? Let me focus in a little bit. Anybody know what those dashes mean? Carter? No? Yes, Maggie's right. That all those lines that have one single dash, those are congruent. So if you go back to this picture, the double lines mean that these lines are congruent, and the single lines mean that these lines are congruent. You know what congruence means? It means they're equal. They have the same length. So in this picture, all 5 of these sides are the same length. That makes sense? We don't know what the length is, but they're all the same. And then the same thing here with these little arcs. That means that all 5 angles are the same. So we actually have a special name for this. This is called a regular polygon. We're going to talk more about that. That's like a square. We'll talk more about that in the future. But a regular polygon just means all the sides and all the angles are the same. An equilateral triangle. Okay, so now back to our problem, though. Is it linear? Well, I think it would be linear if it didn't have these little add-ons. You see these little add-ons? I think that prevents it from being linear. Those little extra pieces. You see those? Because you can't rotate, you can't flip or fold it and make it fit. But what about rotational? Yeah, this definitely is rotational. 360 divided by 5, the number of endpoints is 72 degrees. We've done this already. 144, 216, and 288. All the ones less than 360. Okay. So again, in your mind, you want to be able to envision you're pulling that out of the paper, you're rotating it 72 degrees, and then you're putting it back in. The definition actually says maps onto itself. All right, let's go to the last one, number 9. All right, so let's see. Any lines of rotation? How about, does this look like? No, because that point would match up there somewhere. No. How about here? No. How about from opposite corner to opposite corner? I don't think there's any lines. 0 lines of symmetry. How about rotational? Well, if we rotate it 90 degrees, it would look like this. That doesn't look, that's not the same. If we rotate 180, another 90, it would look like something like that. I don't think there's any rotational either. And so I'd say no rotational or none. So that trapezoid doesn't have any. Okay? All right. You getting the idea of it? What if you were going to make your own picture? You're thinking through things. What about going through right above Bo back there? Bo, can you point it out? How about the IU symbol? So if you look at that, I mean, I'm not going to do it justice, but you know, you've got the U here, and you've got the I here, right? Okay, so how about rotational symmetry? I don't see anything other than the 360, right? But what about lines of symmetry? I see at least one, right? Colby, right in the middle? I don't think I see any others, though. No? Okay, how about a letter of the alphabet? How about the letter Y? Down the middle. I'd see one. How about rotational? No. Okay, how about, well, here's a tough one. Capital N. Okay, rotational. I agree with Colby. Rotational. It doesn't want to be 90. It doesn't want to be 90, but 180. That works. How about any lines of symmetry? Yeah.
Wouldn't 180 be the line going this way instead of that way? So it'd be like, I don't know. Yeah, it would be like that.
On a cap, on a lowercase n, I think that's what you're saying. This is kind of a capital block n.
Yeah, but since the line's going that way, wouldn't if you were to turn it 180 degrees?
No, this goes up to there. So it would look exactly the same.
Yeah, that's right.
Okay. How about line? Anybody got a line symmetry? What if we did the line like this? Would that work? No. It kind of seems like it should, but it doesn't. Okay. So sometimes it just takes some investigating and looking at all. What about the letter W? I see a line. All right, what about the letter? Yeah. 180 again, just like the N, right?
Yeah.
What about line symmetry?
No.
None.
Because if you reckon a Z
Is-
is like a 99 piece of an N.
That's it. Do you see any that would have both? Is there any letter that would have both line and rotational? Bo?
Well, there's two. There's X and there's O.
That's right. They're the only two. They would have both, line and rotational. What about
Yeah, that would be 180.
what about oops. What about the letter V?
No.
Only linear, right? You get the idea. So you're picturing different figures in your head trying to determine if it's line or rotational. Okay, here's your assignment. You should be able to get it submitted. By the time you're done, I should have the canvas ready for you. Page 106, 1 through 14, and number 16. Don't have to do number 15.